Hello, everyone. My name is Sraddha Uppili, and I wanted to thank you sincerely for letting me present my summer research on the automated recognition and quantification of M1, M2 macrophage ratios in meningioma using machine learning. Meningioma is the most common type of brain tumor, and it forms in the meningothelial cells lining the brain and spinal cord, as seen in this image here. There's up to a 32% chance for meningioma to recur within 15 years of initial diagnosis, which means routine MRIs are used every year to detect as early as possible for any recurrence possibilities. Meningioma is normally benign, but it can affect the adjacent brain greatly, and this can be quite debilitating depending on its location and size. Macrophages are a specialized type of white blood cell, and there are two key types I focus on in my research. M1 macrophages inhibit cell division, and M2 promote cell proliferation. This is an immunohistochemical slide of a meningioma patient. The M1 macrophages are circled in red, and the M2 macrophages are circled in green. M1 macrophages are characterized by CD68, and they're stained in green and blue. M2 macrophages are characterized by CD68 and CD163 and are stained in green, red, and blue. Previous studies suggest that macrophage ratios act as a predictor for meningioma recurrence, but they are not routinely used by pathologists. My first aim is, can we automate the process of M1, M2 macrophage detection? My second aim is, can this methodology be incorporated into a larger algorithm to efficiently predict tumor recurrence? I used 159 immunohistochemical slides from 50 meningioma patients for my project. I split them into train, test, and validation sets using a Python code to reduce bias, and I made over 2,700 M1, M2 cell annotations over 111 training images using the Fiji LabKit and Pixel Classification plugin. As you can see here, this is an image of my manual classifications, and this is the pixel classification. I used a Python implementation for my model called Stardust, which is used for star convex cell detection. As you can see here, the middle of the cell is characterized by a point with different rays coming out of the point. Areas of darker green are higher confidence that that is in fact a cell, and areas of lighter green are lower confidence, creating this circular oval cell type of shape. The preliminary results show that the highest accuracy score is around 0.73 in the training set, which indicates model overfitting, meaning that the model does not do as well with the validation dataset. The Jacquard index score versus the threshold tells us the prediction versus ground truth overlap, and the index score of 0.52 at 0.9 threshold tells us that the model is partially aligning with the ground truth, meaning that it is able to detect M1 and M2 macrophages in an immunohistochemical slide. To conclude, this is one of the first M1, M2 detection models in neuropathology. And although the accuracy was lower than expected, it gives a great proof of concept of what's to come. Further comparisons between previous research and model results are going to be used to test accuracy, as well as collecting more meningioma immunohistochemical slides to increase the number of data points and increase the model's confidence. Some future directions for this project include creating a graphics user interface for patient and physician use to upload immunohistochemical slides and get the appropriate information, as well as expanding to other cancers, since tumor-associated macrophages are not localized in one part of the body, meaning that they can be used as a diagnostic throughout. And finally, 3D tumor modeling can serve as a really important tool for tumor resection and other treatment options. I'd like to thank the Project NeuroArm team for all of their support, as well as the NSERC Brain Create grant for giving me the opportunity to do this amazing research over the summer. Thank you so much for listening, and I really hope that you enjoyed my presentation.